Good afternoon, and welcome to the video that we're going to use for helping to introduce the chemistry topics that we're going to be talking about as part of our biochemistry unit. So today's topics are going to be more of an overview of chemistry, and then we're going to move into some of the chemistry of water and why it applies to the things that we're talking about in science. So let's go ahead and err in the science of biology. Now let's go ahead and get started. I like this intro slide. And because of the fact that you're seeing a molecular version you're seeing a few molecules at the molecular level where you see the individual atoms that make it up, definite chemistry. You can see the phospholipid bilayer going on here, so we're talking cell membranes and components of cell membranes, and then the good old stink bug, just because of chemistry, that they can smell so bad. And then as I'm going through this, I want to give some credit to Kim Foglia, who is the individual that put these particular PowerPoints together. She was a pioneer in AP biology. Unfortunately, she passed away a couple of years ago, but her memory definitely continues on in the AP community. So thank you to Kim for helping to make this a better PowerPoint than I could have put together myself. So let's go ahead and get started. So why are we talking about chemistry right now? Well, you guys, if it weren't for chemistry, there wouldn't be any biology. All right, so chemistry is really the foundation behind the study of biology. We wouldn't have all the biological molecules that we have. We wouldn't have things being able to interact the way that they do if it weren't for the basics of chemistry. Right? And so one of the big things we're going to get into today deals with water. So dating back to your chemistry years, let me give you a disclaimer at this point. If you have not taken chemistry with Mrs. Ritter or myself at this point, you are, unfortunately, my friend, at a disadvantage. I'm teaching this as if you have a chemistry background. If you don't, make sure you let me know. We'll sit down. I can go over things more in depth. This might seem kind of fast, but I'm assuming you have at least some sort of chemistry background. So once again, if you are stuck with this and you're saying, whoa, that was way too fast, make sure you come and see me, and we'll slow it back down. And even Ariel understands that she's part of this chemistry thing. You guys said you wanted to see her, so here she is. And she gets it that this is all about her, because everything's all about her, so she wanted to be part of this as well. All right, so when we talk about chemistry, the basis behind the chemistry is the periodic table. So when we look at the periodic table, in the world of biology, we can look at 10 specific elements as the main elements of life, and we can really center in on 4 of them, and then there's the 6 others. And so carbon, hydrogen, oxygen, and nitrogen are the main components of life. Now, back in general bio, if you took it with Mrs. McKinley, Mr. Shansker, and myself, we talked about CHOMPS, trying to get you to recognize the 6 essential elements for life. We included phosphorus and sulfur because of the fact that they are also components of some of the amino acids, and they're part of, at least the phosphorus is part of nucleic acids as well. I hope I said nucleic acids. I may have said amino acids. Let me try that again. The sulfur is a component of some amino acids, whereas phosphorus is a component of nucleic acids. And so they're among the macromolecules, and that's what we talked about in the past. Nitrogen, magnesium, calcium, and potassium are also trace elements, and there's some other ones out there as well. If you're familiar with the salt that you're putting on your French fries, they iodize that because there's a particular structure inside your throat that requires iodine. If you don't get enough iodine, you get this big, huge lump called goiter on your throat, and it's not necessarily the thing that's going to help to accessorize all your scarves and things that well. So it's okay to have a little bit of salt so that you can prevent yourself from having that goiter. All right? Now, when we talk about chemical reactivity, atoms want to do one of 2 things. They either want to fill their valence shell or they want to empty their valence shell. Well, what the heck's their valence shell? Just a reminder, their valence shell is their outer set of electrons. So they either want to have a full set of outer electrons, and typically we talk about them wanting 8, unless it's hydrogen or helium, then they want 2. Or they're willing to get rid of them to make it so that it drops down to, it takes their partial shell, makes it so it no longer has any electrons in it, and now the shell that is a lower shell for them becomes the outer shell, and that one is already filled. So we're looking at chemicals or elements are reacting in order to satisfy their outer valence shell, so their outer octet. And so if they don't have that, they're going to want to chemically react. And when they talk about chemical reactions, we're talking about bonds breaking and then bonds potentially reforming. All right, so we can see an example here of this electron is getting transferred to another element. And then here we can see two electrons being shared. So we have an ionic bond forming here, and we have a covalent bond forming here. So when we look at their valence shells, you can predict what their valence is based upon their position on the periodic table, not including the transition metals. And so elements in the same column, which we call families, they're going to have the same valence. And that's going to cause them to have similar chemical properties, which means they will react similarly as each other when presented with different elements. So, for instance, all the elements in the oxygen family are relatively reactive with iron. The halogens here, fluorine, they are all relatively reactive with the alkali metals and the alkaline earth metals because they have 7 valence electrons and they want to get themselves to have 8 to fill their outer electrons. Well, these only have 1 in their outer shell. They want to empty that out because then they'll have a full octet as well. So the best way to empty this out is, hey, I have 1, I'll give it to you, and now you're happy because you have a full set because that'll make it so you have 8. This is happy because for this particular metal, the outer set will then have, let's look at sodium instead, will then have 8 as well because it's donated this one on the outside to here. And so all these chemical reactions are a result of them trying to do things to make it so they have a full outer shell of electrons. You notice the noble gases. They're not very reactive because they already have a full outer shell. I said earlier helium wants 2. The outermost shell, they have 2. Neon wants 8. Outer shell already has 8. Argon wants 8. Outer shell already has 8. Therefore, it is not looking to chemically react to fill that shell. Therefore, these are considered inert because they already have the outer shell that they want to have. The rest of them are going to do things to try to make it so that they can fill that outer shell. And your more reactive ones are your halogens here as well as your alkali metals. And so some food chains are going to be based upon this oxygen being removed from the water to be used for structures. Same thing when we talk about things that use chemosynthesis, using the sulfur from the hydrogen sulfide, dihydrogen sulfide. So when we talk about bonds in biology, there's different types of bonds. We have our weaker bonds that are a result of not necessarily elements interacting with one another, but it's a result of interactions within the particular molecule. And so some examples that would be hydrogen bonds. Hydrogen bonds are the result of an attraction between the positively charged end and the negatively charged end on a particular water molecule. If you look at the shape of the water molecule here, what you'll see is the oxygen end is relatively exposed, and then the 2 hydrogens are relatively close to one another on one particular side of the molecule. So when we look here, there's more positives on this side of the oxygen and none on this side. Therefore, this side is slightly negatively charged, and we use this little, I can't remember the Greek symbol name for this little squiggly thing with a negative sign to show that this has a partial negative charge, whereas this side, because of the hydrogens, has a partial positive charge. Well, so what? Well, what that's going to do is that's going to cause this hydrogen on this water molecule to be weakly attracted to the oxygen on this water molecule. And then you get all kinds of other water molecules that are doing the same thing. The hydrogen ends of one molecule will be attracted to the oxygen end of another, and you get all these water molecules sticking together. When we talk about the weak hydrogen bond in DNA, we talked about between the base pairs. Well, that's a result of differences in what we call polarity. And so then because of this polarity, you're getting differences in charges on ends of those bases, and then that causes a weak attraction between them. We also get hydrophobic and hydrophilic reactions, which are a result of it being water-loving or water-hating. We'll get into that here in a few moments. You get van der Waals forces because sometimes because of these differences in charges, it causes things to move slightly in the atom, and therefore They're going to have it so at times it's charged more positively here, and then at times it's not as charged as positively there. And so because of that, it's constantly changing. We call those van der Waals forces. I'm not too concerned about the van der Waals forces. Just recognize it's one of the weaker interactions. A lot of chemists will say don't call these weak bonds, call them interactions instead. And then your stronger bonds are your covalent bonds and your ionic bonds. Covalent bonds are a result of electrons being shared, whereas ionic bonds are a result of electrons being transferred between differently charged particles. So we can see a covalent bond forming here between two hydrogens. All right, so then when we talk covalent bonds, we can also take them and break them into two different classifications. They can be nonpolar or they can be polar. Nonpolar means that the electrons between all of the atoms that make up the particular bonds are equally shared. So when we look here at a methane molecule, this is your natural gas in case you're not familiar with that. Here's your carbon, and you have 4 hydrogens attached to it, and it's all covalently bonded, while the electrons between the hydrogen and the carbon get equally shared. The electrons between the carbon and this hydrogen get equally shared. And all the way throughout, we get equal sharing of those electrons. So there's not any ends that are more positively charged or more negatively charged. It's an even distribution throughout the entire molecule. All right, so these are balanced, they're stable, they're great for using as building blocks. And so you can see this come back a little bit later on. All right, so good examples of these are your hydrocarbons. Methane is a good example. Propane, octane. And if we take these and we start combining many of them together, this becomes the building blocks for making carbohydrates, building blocks for making proteins and lipids and nucleic acids as well. All right, so when we typically look at your hydrocarbons as well, there's a lot of energy stored in them. That's why we burn them. You heard me say propane and methane and octane, all great fuels. Paraffin, which is most of your candle wax, is once again an example of a hydrocarbon. A lot of energy associated with it. That's why we burn them for the light, and we get a little bit of heat out of it too. Now, a polar covalent bond is instead of having equal sharing of everything, you get an unequal sharing of the electrons. And so what's really going on in the water molecule here is the oxygen hogs the electrons more than the hydrogen does. And as a result of that, it causes this difference in charge on different ends of the molecule. So the oxygen is being more of an electron hog and pulling them more towards it and taking them away from the hydrogen, causing the hydrogen to have a more positive charge and causing the oxygen end to have a more negative charge. And then as a result, when you bring in two water molecules close to one another, they're going to have the hydrogen end attracted to this oxygen end, and then another oxygen end of a water molecule will be attracted here, another oxygen end of a water molecule will be attracted here, and then you get this going on and on and on, which is why water is sticky in the first place. Water likes to stick to itself, and we'll get into that when we get into the properties of water here in just a few minutes. And so the reason why this likes to pull the electrons more is because it has a greater electronegativity than the hydrogens. Electronegativity is the want. It's a weak way of saying the desire to have greater amount of electrons. Oxygen wants more electrons. It is highly electronegative because of it. Hydrogen does not want electrons as bad as oxygen. Therefore, it is less electronegative than the oxygen. Right? And so we've established that water is what we call a polar molecule. Right? And so when we look at the properties of water, it's really the polarity of the water that has the big impact on why water has the properties that it has. All right, so I already discussed hydrogen bonding momentarily. Well, hydrogen bonding is extremely important in the world of biology. It helps to describe, once again, all these unique properties of water. And so we're going to get those properties here in just a few minutes, and hopefully that'll make a little bit more sense. So just to reiterate that polarity is a result of differences in charges on different ends of the same molecule, and then that can cause weak bonds to form between adjacent molecules. All right. We also will often see this occurring when you have an OH, and so if you don't remember what an OH represents, it's called a hydroxide in larger molecules. And so you're going to see that when we start getting into the proteins, and we talk about the interaction of proteins and how they fold, the hydroxylase can have a big impact because it makes certain areas of the protein become polar, whereas other areas may be more non-polar. So that's where we get the hydrophobic and hydrophilic interactions. All right, so hydrogen bond is not a strong bond, and that's why when we talked about it back in bio, we called it a weak hydrogen bond. And when we did the little simulations out in the hallway, we used a little pinky hold in order to signify the weak bond versus actually holding hands to hold together the stronger bonds. Right, but these weak bonds, very common in bio, and you'll be seeing that here quite a bit. So once again, I mentioned earlier about the base pairs. So we have our base pairs. What holds these base pairs together is this hydrogen bonding. All right, so now that you've gotten a little bit of a basis of the chemistry, now let's move into some of the properties of water and what makes water unique. Because you always hear about water being the most important compound out there that provides for life. The reason why we believe life doesn't exist on other planets is because of the fact that we have not found water in a liquid form for them to use. And that's one of the big studies with what they're doing with Mars, with the rovers. They're trying to figure out, hey, is there evidence of liquid water at any time? Because if there is, there might be able to find evidence of life existing there at some point as well. So why is water so important? Well, you guys, you're composed of cells. And guess what composes much of the cell? A lot of the cell is in water. When you think about the cells inside your body, they're bathed in blood. Guess what most of blood is made up of? It's made up of water. Most of the components inside the cell have water as part of the cytosol, part of the cytoplasm that everything else is sitting in. All right, so water is extremely important for life that occurs inside and outside of the cell. All right, so we've talked about the hydrogen bonds and the polarity of it. So if I haven't hammered that enough at this point, I think you should get the point in case you're not picking it up, that the whole polarity thing is extremely important. The water ends here attached to the hydrogen, so you can see a good example with multiple molecules of water coming together. So you see the hydrogen end getting attracted to the oxygen end here, this hydrogen end getting attracted to the oxygen end of this one getting attracted to the hydrogen end here, and this continues to go on with millions of molecules, trillions of molecules, not just one. Right? And so as a result, you get a sticky molecule. And so we can see here, when we look at the beaker full of water, they all end up sticking together. They also stick to the sides of the glass. So we're going to be getting into that here in just a few minutes too. That also explains when you pour water out, does just one or two molecules fall out? No, it all sticks together and you get the entire volume of the water pouring out until you change the angle of that container so it no longer can fit, or it can no longer pour outside of the container. So, yes, water is the elixir of life. Why? Well, it has some pretty unique properties. We'll list all these at once. And I apologize, there's sounds playing and there's nothing, I didn't take the time to cut out all the sounds, so sorry if that's been annoying. Special properties of water, cohesion and adhesion. This is what results in surface tension and something we call capillary action. So we're going to get into that here in just a moment. It is a great solvent, which means it dissolves many things. Water, in fact, is considered the universal solvent, which means it will dissolve more substances than any other. All right, and that helps with the whole hydrophilic and hydrophobic kind of interactions. It has a lower density as a solid, whereas most substances have a higher density as a solid, which means ice will float on liquid water. It has a very high specific heat, which means it can store tremendous amounts of energy. And it has a high heat of vaporization, which means it heats and cools very slowly. So let's take a few minutes and look at each of these particular properties. All right, so cohesion and adhesion are two terms a lot of people get mixed up. Cohesion is the hydrogen bonding that happens between molecules of water and only molecules of water. All right, so water's sticky because of this. So the polarity of the water results in water sticking to one another. That is an example of cohesion. Ariel doesn't want you guys to see me guys anymore. All right, and so this is what results in surface tension. Because of the water, if you can't see me, I apologize, or maybe I don't, maybe it's better for you, is what this whole water sticking to itself is what causes surface tension to occur. There's a tremendous, well, not a tremendous, there's enough force in those interactions, in those polar interactions, to make it so that the mass of the water strider here will not push through to break those bonds, and therefore the water strider is able to walk on the water. Alright, think about when you drink from a straw. Once you get that siphon and it starts to flow, it will continue to grab more of those and pull it through as well. Alright, adhesion, on the other hand, is the attractions between water and other substances. Alright, a good example of this is capillary action. If you're not familiar with what capillary action is, it's similar to when water climbs up a paper towel or a cloth. If you take a thin tube and stick it to a droplet of water, when you put it on the droplet of water, you'll watch the water actually run up into the tube. That's capillary action. You get these weak interactions that cause it to stick to the glass, and then because it's sticking to the glass, it's going to stick to the water's going to stick to the glass, the water will also stick to itself, and it continues to move up as a result. This is also the reason why you get the formation of a meniscus in a graduated cylinder, because of the adhesion between the glass and some of the water molecules. This is also how water gets from the roots to the very top of the tree. So let's check this out. So transpiration, getting water to be able to evaporate out of the leaves, is a result of cohesion and adhesion. So we can see here it's coming in through the roots. Because of cohesion, the water is going to stick to itself. It's going to stick to other water molecules. Because of adhesion, it's then going to stick to the walls of the vascular tissue, and then it's going to continue to draw up because of that capillary action. So as it draws up the walls of that vascular tissue, the water is going to stick to itself, and it's going to continue to move up this entire system until it gets to the leaf. Then once it gets to the leaf, it's going to be in the leaf, and when it's no longer needed, or the heat from the environment makes it so that it gets evaporated, it then has little places called stomata where it can exit the leaf and evaporate out into the atmosphere. So it's almost like an evaporative cooling like we use for us. Water is a solvent of life. What's that mean? That means water dissolves things. Alright, polar water is going to dissolve other polar things. Well, some good examples of other polar things are anything with a charge. So anything that's made up of ions is a good example of something polar. So water is going to dissolve various salts. When we talk about this dissolving, the solvent, we call that is the technical name for things that do the dissolving. Solutes then are the things that actually get dissolved, whether it's the sugar, whether it's salt, whether it's the medicine that you took, it's getting dissolved into the water. When we combine the solvent and solute together, we then call that a solution. Alright, so what kinds of things dissolve in water? I already told you. Things that are polar, just like water. What we call that is a hydrophilic substance. Hydro meaning water, philic meaning it loves it. So substances that have an attraction to water, we call them hydrophilic. Well, if water's polar, and you've heard the term like dissolves like, that means if water's polar, it's probably going to dissolve things that it's like, which means it's going to dissolve things that are then polar. What doesn't dissolve in water? Things that we call hydrophobic. You've probably heard the term phobia, so it shouldn't be anything new, I don't think. These are substances that don't have an attraction to water. In fact, they don't like water. So when we look at some of the examples of hydrophobic substances, hydrocarbons. Look at all these carbons and hydrogens. You have butters and oils and fats. When you put it on when you're washing the dishes, all the fats kind of sit on top of the water because they don't like the water. They're trying to get separated from the water. They're hydrophobic. You have to add the soap, which breaks the surface tension and allows for it to be dissolved. So Are hydrophobic substances going to be polar or non-polar? Well, for the most part, they're going to be non-polar because they don't want to be dissolved by the water. All right, so this is why the fats and your phospholipid bilayers, that makes up waterproof coverings. Your skin, it repels the water because of the membrane that makes it up, it being hydrophobic. So it doesn't let the water dissolve into it. That'd be bad. Think about it. If you got rained on and it all dissolved into you. Yeah, not pretty. Ice being a big one. And think about the fact that ice floats. If ice didn't float, that'd be terrible for life. All right? Almost every other substance is more dense when they're solid than water. Well, why does ice float? Let's take a look at some of the components of ice. If you look at liquid water here, because of the polarity, it's going to stick to itself. However, when ice forms, because of the hydrogen bonds that go on, it forms more of a crystalline structure. And what that crystalline structure is going to do is it's going to increase the volume of the water. Well, because you're getting an increase in volume, it's going to take the density and actually decrease it. In most cases, you don't get this. You get them actually to compact closer together, so you're decreasing the volume. Well, in water's case, because of the way it forms those hydrogen bonds between each other, it actually causes this volume to increase when it changes to a solid. So it's forming a crystal. Well, why is this important? You guys, a couple of things. You wouldn't get layering of water currents based upon temperature if it weren't for differences in density. The water towards the top is going to be warmer, and at some point you're going to get some shifting going on. I don't want to get into this part because we talked about it back in the ecology piece, but I'm not too concerned about that piece. What I really want you to recognize is if you didn't have ice being less dense than the water, then the ice would start at the bottom of the lake and form up. Think about that. If it didn't form at the bottom and move its way, or if it did form at the bottom and move its way up, then all those living organisms, all the plants would die out right away. Then you have all these animals that would eventually end up on the surface, and then they die off. That's not cool. We don't want that. So actually the ice is forming at the top, and then forms an insulating barrier that's going to then make it so that the water underneath will not get to the point where it's all going to freeze, and so you'll have a barrier for life that's available during the winter season. I have a slide here that shows that a little bit better. I thought I had another one, but I guess I don't. And so then because of the sinking of the cold water that's going to happen during the autumn, you're going to be getting this turnover that's going to take the nutrients and help recycle it as well. It's also going to allow for more dissolved oxygen to enter into the lake prior to it becoming frozen over, and which is going to give and because you're slowly cooling it, and when you cool the solvent, it allows for more gas to actually be dissolved into it. So if you do that process slowly, you're going to get a tremendous amount of oxygen stored in there. In fact, enough to be able to last the 4 months when the ice layer is formed over the top to be able to support the life of the living organisms in there. Next one is going to be specific heat. Specific heat is just a way of saying that water likes to maintain the heat that it has. So it takes a lot of energy in order to continue to raise its temperature or to cool its temperature. You've got to remove a lot of energy. And then a lot of energy can actually be absorbed into the water as a result. Alright, so water has what we call like high specific heat. It takes a lot of energy to heat it up. It takes the removal of a lot of energy in order to cool it back down. And so the water really helps to moderate temperatures on Earth, and it makes it so that the climate doesn't drastically change year after year after year because of the water in the atmosphere to help hold that kind of as a buffer to maintain the climate that we have. The last one, and then I'm going to call it quits on this video, is water has a high heat of vaporization. What that's going to get into is you have two areas here when we look at phase changes. So we're starting with ice here, and then it goes through a period where the temperature no longer increases even though you're adding energy. This is something called the heat of fusion. That's the energy needed to change it from ice to liquid. or how much energy you need to remove to change it from liquid to ice. And then eventually, once it's all changed to liquid, it's going to continue to have its temperature go up as it's absorbing more and more energy. Then you're going to get this long period where the energy is still being supplied, but the energy is being used to help convert it from being a liquid to a solid. This takes a tremendous amount of energy to create or to transition it from liquid to solid. The amount of energy required to do that, we call it the heat of vaporization. So that means when it does finally evaporate, there is a tremendous amount of energy stored in those water molecules at the point of evaporation. This is extremely important for helping to cool your body. So when it gets out to your surface as a liquid, and then it relatively quickly evaporates out. Well, if there's a tremendous amount of heat stored in that water when it evaporates out, that means you're removing a tremendous amount of heat energy out of your body. So what a great way to be able to moderate your temperature. And we call this evaporative cooling. We're taking our cooling systems in our body for warm-blooded organisms that are taking advantage of this heat of vaporization. Panting with dogs and cats. That fits into that as well. And I think this is going to be a good spot for us to start to call it good. So we'll get into a little bit more with the pH. I think I'd rather talk to you about the pH when I'm there with you. And I think in the next video what we'll start getting into is talking about some of the macromolecules. Alright, so I think this is a good way to end it, and I like to totally put this together. So do one brave thing today, and then run like hell. Have a good day, guys. Have a good weekend as well.